Hello and welcome to my disc talk. Sinkless orientation is hard also in the supported local model. This is joint work with Ami, Joel, Stefan and Jukka. So the context of this work is Sinkless orientation in the local model. So in the Sinkless orientation problem, you're given a graph G and the task is to orient the edges of the graph so that no node of degree 3 is a sink. We'll ignore nodes of degree 1 and 2 for technical reasons, basically. So Sinkless orientation is a canonical example of a problem with intermediate complexity. So it has complexity log n in randomized local and log n in deterministic local. And it's also an example of a problem where randomness helps exponentially, or by log n over log n factor if you prefer. And moreover, it was one of the first problems where we saw this round elimination formalism for proving lower bounds in the local model. Okay, so that's Sinkless orientation, but what is supported local model? So supported local is basically a strengthening of the local model, so it's a stronger model. In this model, we are given the communication graph G beforehand, and this is known to all nodes. So you can think about the communication graph being sort of fixed, and all nodes know that we are working on this communication graph. And then the input graph H is a subgraph of G. So basically, which edges are part of the input graph is only known locally to the nodes, and the task is to solve a problem on this input graph H. And all the edges of G can be still used for communication even if they are not part of the input. So just to make this super clear, for example, here we can see what this highlighted node can see in the supported local model. So basically it knows what all the edges of G are, but it only sees inputs in its local neighborhood. So one might ask, why is this an interesting model? So originally this was introduced in the context of software-defined networking, and the basic idea is that this communication graph G corresponds to a physical network infrastructure which is fairly unchanging, and the input graph somehow corresponds to the logical state of the network, for instance which communications links are available at this time or something like that. However, it turns out that this is an interesting model also for lower bounds in supported local and also in supported congest. And a sort of natural question, of course, here is, from a theoretical perspective, how much does this knowledge of the communication graph G, i.e. the support graph, help in solving various problems? And it's known, for instance, that symmetry breaking can be done in constant grounds using the support. You can just color the support graph beforehand or so on. Okay, so in this work, what we do is we show that Sinkless orientation, deterministic Sinkless orientation, requires log n rounds in supported local model. And this holds even for support graphs of maximum degree 5 and input graphs of maximum degree 3. And this is tight because you can run local algorithms in supported local. So one may ask, why is this interesting? So this shows us that the exponential gaps from between randomized and deterministic complexity also exist in supported local, so you cannot just use the support structure to de-randomized algorithms. On the other hand, what this gives is a new and very simple proof for the local lower bound for deterministic Sinkless orientation. Okay, so this is how the classical proof goes. So you start from the local model and you go down into the randomized port numbering model without unique identifiers. And then you do this random elimination thing where you basically, in this case, have to keep track of the success probabilities and it gets tricky, and then you prove that you cannot solve this problem in 0 rounds, and then you basically derive a contradiction to show that Sinkless orientation is hard in the port numbering model. And since you can use randomness to generate unique IDs, you can basically lift this lower bound to randomized local. And then to get this log n lower bound for the deterministic case, you also use this cap theorem of Chang et al. To basically prove that since there are no problems between log star n and log n complexity in local, then this log n randomized lower bound implies log n deterministic lower bound. And one of the key issues in this proof is that it seems to be very difficult to deal with node identifiers in this round elimination framework, because they can leak extra information that's difficult to handle in the round elimination. So what we do instead is that instead of starting from the local and going to the weaker model, we start from local and we go up into a stronger model. And this, strangely enough, makes the proof easier. Alright, so let's talk about the proof itself. So actually what we will do is we will prove this theorem in an even stronger model than the supported local, i.e. in the so-called bipartite supported local, and specifically we do it for a fixed 5 regular support graph. The bipartite supported local model is basically the same thing as the supported local, except we are given a promise that support graph is bipartite, and either black or white nodes are active. Only the active nodes are required to produce output, and the passive nodes don't have to do anything. But we still require that this output is globally consistent and satisfies all the conditions of Sinkless orientation. And basically this is even stronger model than supported local, because you can just run a supported local algorithm in the bipartite supported local, and then all the passive nodes just drop their outputs. Okay, and for technical reasons we encode Sinkless orientation in this model as follows. So basically, so this is for black algorithms, you just flip the colors for white algorithms. So if node orients an incident edge oriented out from it, it will output O for that edge, and if it's directed into the edge, it will output I on the edge. So we can think about the node output of a node as a multiset. For example, if you have a black node outputting orienting 2 edges away from it and 1 edge into it, we think of the output of the node being multiset consisting of O, O, and I. And the constraint is exactly what the Sinkless orientation constraint says. So black nodes are not allowed to output a set of 3 I's, and for each white node the outputs of the incident black nodes cannot label all the edges incident to this white node with O. Alright, so first step of the proof is this round elimination lemma. So the sort of overview here is that we assume that there exists say black algorithm with running time t rounds for some t that is roughly at most half of the diameter of the graph. And we then show that this implies that there is an alternating sequence of black and white algorithms, such that each algorithm in this sequence has running time of 1 round less than the previous one, and this terminates in a 0 round algorithm for Sinkless orientation. Okay, so let's look at this round elimination in detail. So our assumption is that there is a black algorithm AT that runs in t rounds and solves Sinkless orientation. And we want to prove that this implies that there is an white algorithm AT-1 that runs in t-1 rounds and also solves Sinkless orientation.
So how do we define this algorithm AT-1? So let's look at single white node U and one input edge incident to U, with the other endpoint being V. So first of all, let's consider how the output of the node V is determined in this algorithm AT. So basically, what V sees in algorithm AT is this neighborhood, radius T neighborhood of V. Now, what node U wants to do in algorithm AT-1 is basically to figure out what V would be outputting in AT and use that to determine its own output. So what U does is that it basically gathers its T-1 radius neighborhood. What it sees is most of this radius T neighborhood of V, except these highlighted areas on the edge. And what U now does is that it enumerates all possible inputs that could be happening in the shaded region, and then as output it produces the set of all labels that V could be producing under this algorithm T1 for any possible input outside its own T-1 radius neighborhood. And basically the output of the U will be the set of all labels that we could produce. And now we claim that if we relabel these sets of labels as shown on the slide, we will actually get a valid output for Sinkless orientation. Okay, so why is this the case? So let's assume, for the sake of contradiction, that U actually produces output III, i.e. it becomes async. Now this means that the set of possible outputs for these incident nodes all contain the label O. And for simplicity, we can assume that all these sets of labels are actually I and O. So now let's look at the all neighbors of U that are connected to U by input edges. So first, this is the neighborhood that V1 sees in AT, and same for V2 and V3. And now the critical point to observe here is that these shaded regions only affect one of these neighboring nodes. And here we are using the assumption that the running time of the algorithm is less than half of the diameter of the graphs. So there cannot be any cycles that get closed here. So basically, since we are assuming that the set of output labels on this edge between V1 and U is IO, we know by definition that there must be some input setting in the shaded orange region that results in V1 outputting O in AT, because this is how we define this new algorithm AT-1. And you can make this argument for all of the nodes, all of the black neighbors of U. So basically this implies that there is some input under which node U in the original algorithm AT actually becomes async. But this is impossible because we assume that this AT is a correct algorithm for Sinkless orientation. Okay, so that was the first part of the proof. For the second part, we want to prove that there is no zero-round algorithm for Sinkless orientation in the bipartite supported local model. So this step is fairly simple. I will sort of sketch the general idea and leave the details for the reader. So basically what happens here is that you look at any white node, assuming that the zero-round algorithm is a white algorithm, and then by elementary observation you can actually see that there must be at least 3 incident edges to this white node that can output O on some input, so orienting this edge away from this node. And this is because otherwise you would have 3 edges that always output I, and if you just pick those 3 edges to the input, then this white node becomes a sink. So by basic counting argument, this also means that there is at least one black node for which at least 3 incident edges can output O on some input. And then because this is zero round algorithm and this is graph with high diameter, you can basically set up the input so that this black node actually becomes a sink under this input. So to summarize, what we basically get out from this is that if we assume that there is a black algorithm AT that solves Sinkless orientation in T rounds for some T smaller than the diameter of the graph we fixed in the beginning, which is omega log n, then this implies that there exists a zero round algorithm for Sinkless orientation, which is impossible and thus a contradiction. And that's it. Thanks. And for more details, see our paper on archive.